In this section, I'm going to show 6 distributions, 3 discrete and 3 continuous. The first discrete distribution is the Bernoulli distribution. The Bernoulli distribution, we have 2 possible values in the variable x, or the random variable x. One is 0 and the other is 1. Sometimes we call these 2 values failure for 0 and success for 1. And this is equivalent to a city with 2 regions, A and B, or 0 and 1, or we can call the regions failure and success. And in distributions, we always need to take into account parameters. What are the parameters we need to be able to define a distribution? In the Bernoulli distribution, there is only one parameter, and it's called pi. And the parameter pi means what's the probability that to find a success, or what's the probability that the drone will land in region 1. In this case, the probability is 0.2 or 0.20. So the probability of success is 0.2. This is the Bernoulli distribution, and as I said again, is equivalent to the drone landing in one of 2 regions in a city. We saw expansions of distributions, and one of the expansions of the distributions of sample spaces was to let the drone land several times. And this is the equivalent to the binomial distribution. So the binomial distribution needs 2 parameters. Pi, which is equivalent to the one in the Bernoulli distribution that we've just seen, and n, which is the number of trials, the number of experiments, or the number of drone landings. In this case is 3. So even though we start with the pi 0.20, that's a very important parameter, here we are not interested in the probability of landing in a specific region of the city. We are interested in the probability of the number of landings in one region. So here we've got the random variable x takes 4 possible values, 0, 1, 2, and 3, which is 0 landing in region 1, 1 landing in region 1, 2 landings in region 1, and 3 landings in region 1. So that's after 3 trials, experiments, or drone landings, what's the probability that it will land 0 times in one region, 1 time, 2 times, or 3 times? So I've already explained how we expand from using the drone metaphor, but when we use distributions, we have to know the parameter pi is 0.20 and n equals 3 at this stage. So we can see that if the probability of success, or the probability of landing in region 1, is 0.20, and we have 3 trials or 3 drone landings, then the probability that none of these landings or none of these trials is a success is a bit more than 0.5. The probability of finding 1 success is a bit less than 0.4. The probability of having 2 successes is less than 0.1. And the probability of 3 successes is quite small, close to 0. Let's go to the third discrete distribution. This is a categorical distribution, and the parameters that we need is a pi for each of the possible categories. So we've got categories A, B, C, and D. These are the possible values of the variable. And in this case, all the pi's are the same, 0.25. You can see that the sum of these pi's adds to 1. But this is not necessarily the case. It can be that some values are more probable than others. I just wanted to show you one possibility, that is that they are all equally likely. And when the possibilities are equally likely, we call it also a uniform distribution, because the probability is the same in each of the possibilities. Now let's move to the continuous distributions. Now, the most important distribution, the most important continuous distribution, and probably the most important of all distributions, at least in psychology, is the normal distribution. We also call it the Gaussian distribution. And it has two parameters, mu, which is the mean of the distribution, which in this case is 0, and sigma, which is the standard deviation of the distribution, which in this case is 1. Now, when we've got a normal distribution with mu 0 and standard deviation 1, that is a standard normal distribution. So, what are the characteristics of the normal distribution? Well, it is centered in one value, in this case 0, and from that value it is symmetrical. So whatever we find on the right hand side to 0, we find in the left hand side. We can see here that values go from 0 to 7 and 0 to -7, but it's not close there. So it's actually, this distribution can go from -infinity to +infinity. Now, the most likely values are the ones close to 0. 0 is the most likely value. Values between -1 and 1 are very likely as well. And then if we go a bit further, -2 to 2, we've got almost all possible values are within these two. And if we go further from the center, values are less and less likely. The second of the continuous distribution is a continuous uniform distribution. Here we have a value, a variable that has a continuous distribution of the interval that goes from minus or negative 0.4 to positive 0.4. These are the two parameters that are needed for defining the continuous uniform distribution, which is what's the minimum value, minimum possible value, and what's the maximum possible value. In this case, the minimum is negative 0.4 and the maximum is 0.4. So a uniform distribution means that all values within this interval are equally likely. Now, as in the normal distribution, we don't have probability mass anymore, which is we use in the discrete distributions. We have probability densities, as I explained earlier. Now, probability densities do not add to 1, they integrate to 1. If you see here, sometimes this confuses people. It confused me a lot when I was learning about distributions, is that how come values can be, the probability of some values can be more than 1 when they have to add to 1? Well, this is not the case. It doesn't add to 1, it integrates to 1. And if you, in this case, we can see how this works pretty well. We cannot see this very intuitively in the normal distribution, but in this case it's quite easy. So remember that probability density is probability mass divided by the length of the interval of which we have that probability mass. So here we've got the interval. We can take the interval of the full interval from negative 0.4 to 0.4. So what's the length of that interval? Well, it's 0.8. You've got 0.4 from negative 4 to 0 and 0.4 from 0 to 0.4. So altogether is 0.8. So the interval is 0.8. What's the probability mass on that interval? Well, the probability mass is 1 because we've got all the probability is, the total probability is within that interval. Beyond that interval, so values higher than 0.4 and values lower than negative 0.4 have a probability of 0. So all the probabilities within that interval. So the probability is 1. So if we know that the density is 1.25, you can see here 1.25 on the whole interval, and the interval has the length of 0.8. We can tell how the 1.25 was calculated. The total probability mass of that interval is a 1, and the length of the interval is 0.8. So 1 divided by 0.8, that's 1.25. And 1.25 is what we have here. So probability density, remember, is the probability mass divided by the length of the interval in which we have that probability mass. So probability densities do not add to 1, they integrate to 1. And the last of the probability distributions we're going to see is the beta distribution. The beta distribution has possible values between 0 and 1. So it's quite good to deal with proportions or probabilities. So we can have a probability distribution over probabilities. So we are going to see later that the beta distribution combines very well with the binomial distribution. I just want to say here that the beta distribution works in the opposite way of the Bernoulli and the binomial. So imagine that we, instead of knowing, trying to calculate the probability that the drone will land in one area, what we have is some data. In this case, we've got the parameters a equals 2 and b equals 2, sometimes called alpha equals 2 or beta equals 2. What is telling us that we observe 2 landings in a region and 2 landings in the other region. So we've got a city of 2 regions. We can call them success and failure. And the A2 means that we observed 2 landings in the success region. And the B parameter tells us that we observed 2 landings in the failure region. Now, observing only 4 landings is not very informative, so that's why we have this distribution. Yeah, the most probable value is 0.4, 0.5, but there are still values that are away from 0.5 that are possibly likely. So in this case, the probability of success, 0.5 is the most likely, but 0.6 is still very likely, 0.7 is still very likely, even 0.8 has a quite decent probability, 0.9 as well. So the one that is not likely at all is 1 and 0, because we've got at least 2 landings in each of the regions, so it cannot be a probability of 0 or probability of 1. So that's 0. But if this A is 200 and B is 200, this will be equivalent to, okay, I observed 200 landings in the success region and 200 landings in the failure region. Then that means that the most likely probability of landing in the success region is 0.5. So what you are going to observe in that case is a distribution that, instead of being quite broad, it will peak in 0.5 quite dramatically. So values away from 0.5 are very, very unlikely. Values close to 0.5 will be likely, but away from 0.5 will be very, very unlikely.